Hello, I'm Aki Vehtari, and in this video I talk about our paper with Tuomas Sivula and Måns Magnusson on uncertainty in Bayesian leave-and-out cross-validation based model comparison. I will first briefly review the basic terms of the leave-and-out cross-validation, LU, ELPD, which is expected to log predictive density for future data. So we are interested in predicting predictive performance for future data. Since we don't yet have the future data, we want to estimate it with ELPD hat, so which is then the leave-and-out estimate for this true ELPD. And in this paper and talk, specifically, we are interested in when we are comparing differences of two models. So we subtract these ELPDs of model A and model B, and then what is the difference? And then what is the uncertainty then related to this difference? So can we estimate how close this ELPD hat is to true ELPD when we are doing these model comparisons? So here's just simple linear model. True mean is shown, and then we have normally distributed uncertainty around it. There's one realization of the data from this data generating process, and then we can fit a model there. We can get posterior mean and uncertainty so that we have posterior draws, and then when we integrate over this posterior uncertainty, we get posterior predictive distribution shown here with the red, and then we could make predictions with that. And now we want to know how could these posterior predictive distributions would be for new data. And here's example of realization of new data, and we would like to have even like infinite amount of the new data, and that would be the true predictive performance for the new data. But now, before we have the new data, we need to do something with existing data. So we can take one of the data points and leave it out from the data, and then just fit a model with all other observations. And so this is the leave-and-out mean, and it's usually the posterior mean. Leave-and-out posterior mean gets further away from that left-out observation, and then we can compute also the leave-and-out posterior and leave-and-out predictive distribution, and usually this predictive distribution also then shifts away from the left-out observation. Then we want to now use kind of the estimate how good these predictive distributions are, and we use log score. So we have the whole predictive distribution, but we look at it then how well it can predict this left-out observation. Here we first saw the posterior predictive density for that observation, and then if we compare that 0.07 to predictive density for the leave-and-out predictive distribution, it's usually smaller because this predictive distribution was shifted away. So it is more difficult to predict the left-out observation. It's then possible that we can repeat this process. So each observation at its own time is left out, and then we compute these leave-and-out predictive densities. There's practical and information theoretical reason that we take a logarithm of that, and then this is the leave-and-out log predictive densities or log score of these predictions. And we can then just sum these together, and then this is now the ELPD hat, our estimate for the future. Instead of sum, we could also use mean, but there's some benefits of using the sum form. And now this ELPD hat is almost unbiased estimate of ELPD for new data, and reason why it is almost is that now we are using just one observation less to form these predictive distributions. And then the true ELPD, there we would be using predictions based on all the observations. So, but then in this case, it's the difference of only just the whether we are using n or n-1 observations. And so when n increases, then this bias also decreases. We can compare also now this ELPD hat Lu. What if we would have just taken these posterior predictive densities and their logarithm and then sum them together? We see then that this log predictive posterior predictive density has higher value than the leave-one-out predictive density. So it is easier to predict those observations we already saw than those which were left out. We can also look at the uncertainty related to this estimate. And so by taking these leave-one-out log predictive densities, these individual values, computing the standard deviation of those, and multiplying by square roots of the number of observations. And we are multiplying now because we are looking at the sum instead of mean. And then we get this standard error. So this describes how much uncertainty we have, what kind of error we would expect to see when we compare ELPD hat to true ELPD. And this is commonly used, this kind of normal approximation. In model comparison, then we want to compare these ELPD hats from two models or more. I use an example, a logistic regression for predicting probability of switching well with high arsenic level in rural Bangladesh, and we have two models. The first model has, so they, those who well users, they know the arsenic level, and then we use log arsenic, and they know the distance to the next clean well, and how well this predicts whether they switch to the clean well. And then we want to compare this, whether additional education level, does it improve this predictive performance? And if it improves predictive performance, it means that then also the education level affects this decision making. Here we have, so then these individual, these pointwise ELPD values. So on x-axis we have the model 1, and on y-axis model 2. And we can see that overall, if some observation is easy to predict for model 1, it is easy to predict for model 2, so that we get high log predictive density value. And then if something is difficult to predict for model 1, it's difficult to predict also for model 2, so we get low log predictive densities. We can see now that if we compute these sums, that the model 2 has a higher value than model 1, so it seems to be better. We have these uncertainties here, but now these uncertainties are these marginal uncertainties, so how much variation there is along this direction and this direction, while we are interested in variation only conditionally here, as it and since there's this correlation. So we can instead switch to looking at the difference of these pairwise, pointwise ELPDs. So in y-axis we have model 1 pointwise ELPD minus model 2 pointwise ELPD, and then just on x-axis the model 1 to make it this scatter plot easy to read. And we can see now then this difference being minus 14.4, and the standard error is smaller than the marginally. So for the difference, we know the accuracy is better. Now this is kind of making this normal distribution approximation, which is based on that we don't know to even know whether this overall the distribution of these pointwise ELPDs as normal distribution, because based on then the central limit theorem, the uncertainty in mean or sum is anyway more close to normal when we have very large number of these observations to be summed or taken average of. And so we don't have much uncertainty, and it's very normal. And in this case, we would then say that, okay, there's only very small probability that model 1 would be better than model 2. But now, in this paper, we look more carefully than when this normal approximation holds. So we are estimating the difference in the predictive performance for future data. And now we use this standard deviation of these pointwise ELPDs to estimate also then the uncertainty in this ELPD hat, the sum of these differences. And so what is the connection between the distribution from these individual pointwise loop log predictive densities and then the error distribution for this ELPD hat and compared to ELPD? And does this central limit theorem hold? Or when does it hold? There's two relevant papers for this previously, Benji and Crossvalidation. They show that there's no unbiased estimator for the ELPD variance for one model. Actually, we don't care if we have perfectly unbiased estimator. We care that bias should be small and overall the error should be small. But they also show that if the number of observations is small or there are small number of outliers, then these variance estimates can be actually quite bad. And this is also related that with small number of observations or small number of outliers, also the central limit theorem breaks. Another relevant paper is Zhao's paper showing that leave-one-out cross-validation is asymptotically inconsistent, meaning that if we have nested models, the simpler one is the true model, and then we have more complex model with one extra parameter. And then what if this extra parameter, the true value for is 0? When we get more and more data, the predictive distributions of these two models get closer and closer, because now the extra parameter, that posterior, concentrates towards 0, and it doesn't have effect in the predictive distribution. And now it just happens then that these predictive distributions get so close to each other that then this kind of predictive performance estimate with the leave-one-out is not able to make difference between models. In a way, it doesn't matter. It doesn't matter then asymptotically which model we choose if they have the same predictive performance. Zhao did look this also only from the normal approximation point of view, and then we in our paper look also higher moments and what is the relevance here. So in our paper, we have simulation and analytic results. The main example is the models A and B, where then B has this extra parameter beta, so nested models. And then we simulate many data sets with varying n, beta, and outliers. We compute this estimated ELPD hat for the model difference, and then the true ELPD for the difference. And then we have also analytic results, compute these moments and of the relevant distributions. We have certain basic illustration examples illustrating the main behavior. In the first one, this is a clear case. So the plot shows on the x-axis we have the ELPD hat, and on y-axis we have the true ELPD. Each gray dot is simulation result, so one data realization. And so you can see that with different data realizations, the ELPD hat varies, but also the true ELPD varies, because we have learned different things from different data realizations. We also see now that now the model B is clearly better, so that we get negative values, and also for the true negative values. The green line shows when the values are the same, and then we can also see that then overall, on average, we get the kind of the same result. So this is unbiased estimating in a clear case, and this seems also it seems that the uncertainty is approximately normally distributed. Another prototype case is when the models are similar, so beta is 0. So asymptotically the models are exactly the same, but in a finite case we see behavior like this. Now, so the ELPD hat, the values with different data realizations, they are around 0, but most of them are actually now then favoring the simpler model, even if the models are actually the same, with just the more complex having extra parameter. But there's also uncertainty that it is now highly correlated. So when we are estimating that model B would be better, then the model A is actually better. The good thing here is anyway that these differences are very small. So even if we would kind of choose either A or B, the error would be small anyway in our predictive performance estimate. The third prototype case is that we have outliers, and there it is a bit worse. In this case, the outlier is really very strong, and it's something that we usually would see already in before running Lee1 out. We would see in different other diagnostics that there's outlier, and we should reconsider our model. But in the case of outlier, we can get highly biased. We can see now that all the gray dots, they are actually now away from this line where the values would agree. ELPD hat is saying that the smaller model is better, while actually the more complex model is better. And so with outliers, it is possible that we get biased results. Let's look then, how can we kind of how well then these uncertainty estimates for these differences work. So here we have the first case, the clear case. So beta is 1, clearly away from 0. We have relatively large number of observations, and now the bias is very small, and then we pick two example cases. The one we can see now comparing our normal approximation and the true error distribution with histogram. And then the specific point was then that if we have a data realization saying that ELPD is like this, and our normal approximation is like this, and then the true error distribution would be as a histogram. So we can see that our uncertainty estimate is quite well calibrated. And same also for the point 2, the uncertainty estimate is quite well calibrated compared to true error distribution. Then another example where beta is 0, so the models are very similar, or actually kind of the same. And now we have the problem that, like in case 1, our uncertainty estimate is like we are underestimating the variance or variability in the true error distribution, and also the true error distribution is skewed, which the normal approximation doesn't take into account. So normal approximation doesn't work so well. For the point case 2, now we are actually overestimating the uncertainty, but again, there's also the issue that we don't take into account the skewness well. Since there are more simulation kind of the cases on this side, then on average, it happens that we are underestimating the variance, and so on average, we have a bias in variance estimate, and it's underestimated. Even in some cases, we are actually overestimating. Still, the good thing is that the true error is small. So even if our normal approximation fails, we don't make big error compared to true ELPD anyway. So when the models are similar, it's not that harmful that our these uncertainty estimates, normal approximation fails. Unfortunately, it is also that it turns out that it's not possible to estimate the skewness well. So it really is that kind of that we could get maybe just a little bit more out of this, but not much. So it seems that it's most of the time fine to use the normal approximation, just acknowledging that it fails when the models are very similar, but it doesn't harm because the errors are still small anyway. The third case with outlier, so beta is big, but still because of the outlier, the LPD hat is saying that the smaller model would be better. And then again, our uncertainty estimates are not good, but actually now we are kind of, the bias is that big that even if kind of the variance estimate is far, but it's still that we are, because of the bias, it's the bigger problem. And of course, then these kind of outlier cases we should just avoid by making better models. Here's also the fourth case. So the first one was the clear case with beta 1, lot of observations, and now we have kind of clear case, but only small amount of observations. And with small amount of observations, it's not that clear anymore. And with small amount of observations, we start to again see that we can underestimate the variance of the true error distribution. And then it means that leave out cross-validation is not that good for very small observations, but then all inference with small data is difficult. So this is not special just for leave out cross-validation. Of course, by making more model-based assumptions, we can get more out of small data, but all the approaches that would make very weak model assumptions would suffer in the small data case. So our paper has also then these analytic results, and there's more in the paper, but showing, for example, now the skewness part. So we saw that when the models were very similar, we had skewed results, or when we had very small n, we had these cases. So this shows now that with different increasing amount of observations and increasing beta. So when beta is 0, in all amount of observations when the models are very similar, the true error distribution is then skewed. And then when the beta increases, true error distribution skewness gets closer to 0. And so we get closer to normal, and the normal approximation works better. On the other hand, we can look this also what happens when the n decreases. So different colors are now different betas. And so this one is, the blue one here is when the models are similar. And when the n increases, the skewness also just grows stronger. But then for others, depending on how clear this effect is, it goes faster toward the normal, or it might take a bit longer to get towards the normal. And so it just means that if the effect is close to 0, the models are kind of similar in the beginning when we can't infer that so well, but when we have enough information to infer this, then we can see they are different, and then the error distribution of the difference estimate starts to get more and more normal. So summarize. There are then 3 cases where may have problems. The first, the models make very similar predictions. The good thing is that if this ELPD hat is something less than 4, for example, so we know that now the standard error estimate and the normal approximation is not reliable, but the good thing is that the difference is small anyway. Selecting a wrong model has small cost because the true predictive performance would be similar. And it seems that in nested case, the skewness favors the simpler model, which is good. Another problematic case is when the models are misspecified with outliers in the data. It seems that in the nested case, the bias favors the simpler model. And then we should anyway use model checking and model extension to avoid misspecified models. This is part of the Bayesian workflow, and we have separate paper for that too. And the third case, problematic case, is that when the number of observations is small, again, it seems that in nested case, the skewness favors the simpler model. And this is something that we know that any inference that makes weak assumptions is difficult with small n. And then what does small mean? So if these models are well specified so that we already checked that they are now very strong outliers, if the difference is not very small, so the difference is larger than 4, and if the number of observations is larger than, let's say, 100, then the normal approximation is good. It's good to remember that we should not use cross-validation to choose from a very large set of models. So the cross-validation is fine when we have few small number of models and where they kind of most of the time we can see that the differences are big. If the differences are small, we might prefer model averaging. But if we have a large set of model, it's likely that there is kind of too many models where there's too much uncertainty, and then the selection process leads to overfitting. And this overfitting in selection process, it's not unique for cross-validation, so not to worry there. But you can see then our another paper for illustration and projection predictive approach for better variable selection in case of large number of models. And the final slide, again summarizing, if the ELPD difference is less than 4, don't trust the standard error, but the difference is small anyway. Remember to do model checking and model extension to avoid badly misspecified models. If number of observations is less than 100, be extra careful. And here's the reference for the paper. And there's also additional comments in my cross-validation FAQ page. And we'll soon have also more results in a way that how to do easier model comparison when we have more than 2 models, or what to do when the models are similar.